Alrighty, I want to take a look at an example from the end of the chapter. This is a problem that is not assigned on the homework, but it's right next to at least one problem that is assigned. So number 26 says 1 cubic centimeter of a typical cumulus cloud contains 50 to 500 water drops, which have a typical radius of 10 micrometers or microns. For that range, give the lower and higher value respectively for the following. A, how many cubic meters of water are in a cylindrical cumulus cloud of height 3.0 kilometers, radius 1.0 kilometer? So this is a very good problem. I want to walk you through the setup of how to approach this problem. It's a framework that you can use in solving any problem to come. So some of it might seem a little bit more drawn out than you're used to, but I encourage you to try something new, see what you think of it. So I'm going to stop my share so that the whiteboard's a little bit bigger. All right, so there we have it, the whiteboard. And the first step that I think of whenever I am solving a new problem is I want to first draw. So I want to sketch out a picture, and why I want to do this is oftentimes when I'm drawing a picture, I might realize things that I didn't when I first read the words, because words are really hard to take their meaning in. So when you draw a picture, sometimes that can illuminate something you didn't realize at first. So looking at the problem statement, I encourage you to go back and do that. Think about what you would draw. Give you a moment to do that. Now, at the very least, we know this is about a cloud. So I could draw a cloud, right? It's not a particularly good cloud. It looks a bit like a shrub, but that's okay. I could even draw the fact that it has a whole bunch of water droplets in it. So this is trying to take the meaning of the text and put it into a picture form. So connecting the words in it, it says 1 cubic centimeter. The typical cloud contains 50 to 500 water drops. Now that's an interesting description right there, because it says a cubic centimeter. I'm hearing cubic, now I'm starting to think of a cube, right? So I can sketch out a little cube there. Where this is 1 cubic centimeter, and it has a whole bunch of drops in it. This is getting a little more specific to the description of the problem, that within that 1 cubic centimeter, there are going to be 50 to 500 drops. Awesome. Sorry, my writing's a little messy there. Anything else that gives us a clue on things we could draw? Well, one thing you might have noticed is in part A, it mentions cylindrical cumulus cloud. Cylindrical, hey, that's a shape we've heard of before, right? Cylinder, so we could draw a cylinder. It mentions a height and a radius. So this doesn't look super like a cloud, but it says it's cylindrical, so that seems reasonable to me. So I could draw in my radius and then also label my height. Cool. So that is a great start at taking a wall of text and putting it into a more visual form, where even at a glance you go, oh yeah, this is the problem with the cloud and the drops in it, right? So that's already really solid. So that's my first step. The first step is draw, or I want to draw a picture. The next step, which we already started to get into a little bit, is write down what you know. Basically, all the things that the problem tells us, because it packs a lot in there. One of them is this 1 cubic centimeter is 50 to 500 drops. And that we can even write as a conversion factor. 1 cubic centimeter is equal to 50 to 500 drops. Okay, cool. But it also mentions this typical radius of 10 micrometers. So that's the radius of a drop. It's 10 micrometers. Now notice that's not meters. Meters is our base unit. So before I go any further, I'm going to go ahead and convert this micrometer into just meters. And so micro, if you look back at that table that we had, micro is 10 to the minus 6. So what you can actually do is fill in that just this mu, the micro symbol, is 10 to the minus 6. So we could write the radius of the drop is equal to 10 times 10 to the minus 6 meters. And that's how I like to do it to make sure I don't make a silly mistake, because mistakes are very easy to make, as it turns out. All right, let's see. And then it also describes the cloud itself, its height 3 kilometers, radius 1 kilometer. So H cloud, 3.0 kilometers, R cloud is equal to 1.0 kilometers, right? And once again, this is kilometers or kilometers, not an SI unit, but kilo is our prefix for 1,000 or 10 to the positive 3. So I could rewrite these as 3.0 times 10 to the 3 meters, or below, I'd have 1.0 times 10 to the 3 meters. And I like to convert it to my SI base unit right from the get-go, so I don't have to worry about dealing with it later. All right, so this looks pretty solid. We've written down all the numbers. We could also write down any assumptions we're going to make on the problem. But I'm going to say that this is a pretty solid first pass at what we know. The next step is to write down what we want to know. What is the problem asking for? Right, and so here it says, how many cubic meters of water? Let's see, meters of water in a cloud. So that's our question mark, that's what we're trying to find. And as we're thinking about it, it doesn't tell us what quantity it is, but it does give us a clue. Cubic meters, what quantity has cubic meters? Well, volume does. So we're gonna be looking for some sort of volume in this. So this is really useful to figure out where we're trying to get to. Now that we know sort of where we're trying to get to and what we know, we have some pictures to work with, we're going to brainstorm about what tools we have. Or another way of putting this is, what equations do we have to help us out here? So I encourage you to go ahead and pause the video and see what tools you can come up with. What equations might help you out? So go ahead and hit pause now. Did you do it? Okay, well, I'm gonna hope that you did. So as I'm looking at this, one thing I might notice is that, hey, I drew a cylinder and I mentioned a volume. So how do we calculate the volume of a cylinder? Okay, well, might as well write that equation down. Volume of a cylinder is, let's see, the area of a cap, so pi r squared times the height. Pi r squared times the height. Awesome. Anything else we might mention? Well, we were given another radius, and this radius is of a drop. So for the drop, if it gives us a typical radius and doesn't say it's cylindrical, that actually tells us something that we could add to our picture for the drawing. What do we think our drop looks like if they only tell us the radius? Well, what they're implying, and this is where it's really tricky, there's some inferred information, is that each of these drops is actually a little sphere, right? And that sphere has a radius given by our drop. So if our drops are spheres, that's another equation that might help us out if we want to find the volume of a sphere. And volume equations, by the way, are given to you on exams, so you don't have to memorize them. You just have to be able to identify that these are something we care about. So for a sphere, the volume is 4/3 pi r cubed. All right. So these are some pretty solid tools here. With the tools section, we're really thinking about how, right? How are we going to get from point A to point B? And that's where we can look at this and say, okay, well, we can find the volume of the cloud. That just tells us how much total volume there is. We want to get to the volume of the water of the cloud, right? Because we can also find the volume of an individual drop within the cloud, but that's just one drop, right? We need to know however many drops are making up all of the water in the cloud. Because once we know all of the drops within the cloud, then we can figure out, based on the volume of one drop, how much total volume there is of water. And that's where this factor comes into play, right? Which I wrote as a conversion factor up here. We have a way to go between cubic centimeters of cloud, which maybe I should have noted here. This is cubic centimeters of cloud, into a number of drops, where we know if we have 1 cubic centimeter of cloud, we'll have 50 to 500 drops. If we have 2 cubic centimeters of cloud, we'll have 100 to 1,000 drops. This is really convenient. So this may still seem a bit murky, maybe a bit foggy to you, but I encourage you to, let's see how far we can go with this and see if things can come together. So I'm going to tilt this down so we can see a little bit more of the board. I'm going to have to bring the other one up in just a moment. All right, so I'm going to start with the volume of an individual drop, just to get that out of the way. So for the drops volume, we're going to use this volume is equal to 4/3 pi times the radius of the drop, which is this 10 times 10 to the minus 6 meters. All right, and so we can multiply that out with a calculator. Let's see, 10, I like to use the EE button. I encourage you to check it out. So 10 EE minus 6 times 4 divided by 3, and then times pi equals a very small number. Let's see, if I go scientific notation, it would be 4.1888 times 10. Oops, and I almost forgot. Of course I meant to do it. I just put in my radius here, and I left off the cubed. So this is a very different answer than if I remember to cube this. Whoop. So that's a really easy mistake, and that's part of why I write out the sample calculation, so I can make it easier to plug into my calculator and easy to troubleshoot where I might have gone wrong. So let's try that once more. 10 e minus 6, and then we're going to go ahead and cube that. So that's now 1 times 10 to the minus 15. Yep, that sounds right. And times pi times 4 divided by 3. That's more like it. Still a very, very small number. It's just powers of 10 smaller. So I could have left that first part in there. 4.18, and here we really only have 1 or 2 sig figs. It's not particularly clear. I'm going to leave a couple extra for now, because it's always good practice to leave at least 3, leave more than what you have until the very end. So 4.189 times 10 to the minus 15 meters cubed. And that's another place where I started to recognize, actually, when I was writing this, is because it's cubic meters, right? If I didn't have the cube there, I wouldn't get my units of volume. I would just get units of length. So that helps to highlight highlight my mistake. So this is the volume of a single drop of water. It's very, very tiny. Raindrops are pretty small. So this is fairly reasonable. Okay, well, let's take a look then at the volume of the entire cloud and see how we do with that. So this is pi r squared times h. Still on? I am. Awesome. So pi times my radius of the cloud, 1.0 times 10 to the 3 meters, and that is squared, so I'll remember that this time, times the height, which is 3 times 10 to the 3rd meters. All right. So taking a look at this, you can just do this as 1,000 and 3,000, and that's often easier to work with. So that's what I will do here. So pi times 3,000 times 1,000 squared equals now a really, really big number. So 9.42 to start. Times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9. Wow, a billion cubic meters. So this is the volume of said cloud. And at this point, we've made really good progress. So at the very least, even if you don't know where to go from here, you get a good amount of partial credit because you've been able to show that you can calculate the volume of the drop, showing your work, and the volume of the cloud, showing your work. The key here is we want to find volume of water, but not just of one drop of water, but all the drops of water. And to do that, we need to know how big the cloud is. We need to convert the size of the cloud into the number of drops. Once we know the number of drops, we can multiply by the volume of said drop, and we'll have the total volume of everything together. So that's where we're headed. Now these are both in cubic meters, which is great. I really like that. Our conversion factor up here, I'll use the lower one. Conversion factor, meanwhile, is in cubic centimeters, is equal to this number of drops. So this is a problem. We need to make this match the cubic meters in order for it to cancel out, right? So I'll write it down below so that we have it down here. But we could write this conversion factor as if we divide both sides by cubic centimeters. Well, I'll just write it out to start. Let's see. So we have 1 cubic centimeter is equal to 50 to 500 drops. Or 50 to 500 drops is equal to 1 cubic centimeter. But I want to convert this 1 cubic centimeter into cubic meters. So how am I going to do that? Well, we can follow our standard procedure of I want to cancel a centimeter out and I want to convert it into meters. So I'm going to write it like so, with centimeters in the denominator, meters in the top. And then I can look at this and say, okay, I know that centimeters is smaller, so there's 100 centimeters in 1 meter, or 10 to the 2. Now, here's the key. If I do this once, I've converted one of these cubic centimeters into meters. So I'm left with centimeters times meters. This is not yet cubic meters. The only way to get to cubic meters is if I do this same conversion 3 times for all 3 centimeters in this 1 cubic centimeter. So you can either cube this conversion factor or you can write it out explicitly. 1 meter, 10 to the 2 centimeters, 1 meter, 10 to the 2 centimeters. Right, and now we can see that our centimeters do in fact cancel out. Sorry, this is getting so low down here, but our centimeters, we cancel one of them, two of them, and all three of them. And we're left with meters times meters times meters. So that will actually give us our cubic meters as a result. What does this mean? Well, it means that 50 to 500 drops is equal to 1 cubic centimeter, or 10 to the minus 6 cubic meters. All right, sorry, that's getting really low down there. So let's see if we can put this all together and finish it out. So I'm gonna move this for the moment. Put another board in front. So if we want to get the number of drops in the cloud, then we just take the volume of the cloud and multiply that by our conversion factor. All right, so the volume of the cloud we found was 9.42 times 10 to the 9 cubic meters. And now we're going to multiply it by this conversion to drops, which we said that there were 10 to the minus 6 cubic meters in 50 to 500 drops. So what we'll notice is in multiplying this, our cubic meters are going to cancel out, and we're left with a number of drops. So this will indeed give us a number of drops. Before I multiply it though, I'm going to leave it actually as with the times 50 to 500, I'll just divide by the 10 to the minus 6, which you notice will make it extra big. If we're dividing by 10 to the minus 6, we'll have a very large number. So I'm just going to worry about the powers of 10 for now. So 9.42 times 10 to the positive 15 times 50 to 500 drops. So this is our number of drops total. And if we want the total volume of water then it's going to be, go back to the original color, the volume of 1 drop times this number of drops. And at last, we are almost there. So let's peek the volume of 1 drop. It's 4.19 times 10 to the minus 15. Cubic meters times this number of drops, which I'm just going to take all of what's there, remembering the 50 times 500. So 9.42 times 10 to the positive 15, and then times 50 to 500. And the drops kind of just drops out. Like, you don't have to worry about that too much, or you could, if you want, think about this as a volume per 1 drop. So then if you multiply by a number of drops, then that would indeed cancel out. And now we're at the point where we can plug and chug. Conveniently, if you notice, we have 10 to the minus 15 times 10 to the positive 15. So those are just going to go away. You can still multiply it out if you want to double check yourself there, but it won't be that big of a factor. So if we do this once times 50, we'll get one result, and then the other result will just be 10 times bigger. So I'm going to try just doing it once and see how it goes. So 4.19 times 9.42 times 50. And what I get here is, I'll write it out first, 1,973.49, which is purely depending on how I round it up here. That helps to highlight the insignificance of all these decimal places. So how I would actually write this is, in scientific notation, I would write as 1.9 times 10 to the third. The 500 is just going to be 10 times bigger. So I could also write as up to 1.9 times 10 to the fourth. And I need my units in order for this to be meaningful, cubic meters. And that is my final answer. Whew, we made it through the problem. It was a bit extended to show all the steps, but I hope that this will help you as you think about solving problems and the approach that you want to take in order to go about doing that.